This session? Yeah. And hello, everybody. We are going to get started here in just a minute. Okay. All right. Hi, everyone. Welcome and welcome on Zoom for everyone out there in Zoom land. Welcome to our science speaker talk for today, which is featuring the summer 2024 NSF-REU interns. I'm really happy to be here, and I'll just start out with a thanks to our sponsors for the science speaker series, which include Bank of America, Cisco Brewery, and the White Elephant. And let me see if I can, okay. Yes. Okay, cool. So I'm super happy to be here. Thank you for coming. This is always like one of my most favorite and also not favorite sad times of the year because it's kind of the culmination of a whole entire summer of work. But also sad because it means it's towards the end of the summer and folks will be leaving soon. So it's always a little bit bittersweet. But I'm really happy to welcome you here today to watch the presentations of our summer astronomy interns. Everybody is listed here, including their universities, and they'll each be giving about a 10-minute talk today, followed by a couple minutes for questions. And then at the end, what we'll do is if you have more questions that you thought of later or whatnot, we'll just take general questions for everybody. So don't worry if you didn't get a chance to ask your question right away. And we will also be monitoring the Zoom. So for folks who are on Zoom, if you have questions, please go ahead and put them in the Q&A function, and we'll check that in between each talk and answer questions that way. So I'm super excited. As you can see, we've got students from across the country from a big range of different universities. We had over 380 applicants for the 6 spots this summer. So this is an extremely competitive program, I think, as a lot of you know. And the research that everybody is going to be talking about today, you'll see kind of covers from stars all the way up to galaxies in the early universe. And we're going to hear a lot about those topics. And each student was given their own individual research project, and that's really what they spent the bulk of their time doing this summer. Of course, I think lots of you know, we also spent a lot of time up at the Observatory doing open nights, but really the purpose of the NSF-REU, which means research experiences for undergraduates, is to do research. And that's really what the astronomy interns spend the bulk of their time doing when they're here. And so that involves a lot of different things depending upon the particular research project. Sometimes it involves looking at data. Sometimes it involves looking at data from our telescope or from telescopes in space or elsewhere. Sometimes it involves looking at computer simulations. Everybody pretty much works on the computer, no matter what they're working on. And I'll just note that, as you also might imagine, doing an entire research project in a span of 10 weeks is very, very difficult and actually somewhat impossible. And so really, these are more than like final reports. These are more like status updates on where the projects are currently. And so Ginger, there's a couple seats if you want in the, yeah. And so all of the students will be actually presenting their research at the AAS meeting, the American Astronomical Society meeting that'll happen in January next year in Washington, DC. And so that's where they'll be presenting scientific posters of their research. And they worked really, really hard to put these talks together to really try to explain their research topics to non-experts. So to an audience of the public who does not necessarily have a background in physics or astronomy. And so that's really kind of what we're going to be doing today. And so I think I already said the logistical part about how it'll work. Each talk will be about 10 minutes, and we'll have a couple minutes for questions afterwards. And so please ask questions. We love questions here. So whatever questions you're thinking of. And if you're on Zoom, I encourage you to put the questions in the Q&A, and we will monitor that between each talk. I also, before we get started, I want to give a big thank you to our summer 2024 affiliated astronomers, and you can see them here on the screen. Dr. Rudy Montes from the Center for Astrophysics, Dr. Cassie Lacos, also from the Center for Astrophysics, Dr. Monica Rilano at the University of Granada in Spain, Dr. Dave Principe, who's actually here with us tonight from MIT, and Dr. Lindsay King, who's at the University of Texas at Dallas. And each of them have brought a project and helped mentor one of our students this summer. And we really do this program in part so that we can offer a wide variety of different projects in different topics and different fields. And so these are the folks that worked with us this summer. And you'll hear a little bit more about them at the start of each talk. So I think that was all I was going to say. And with that, I'm going to, first of all, make this disappear for our, so this is not in the way. Maybe I'll put it down here. And then I'm just going to do some technical things here so that we can see the screen okay. And if you are in Zoom world and something's going wrong, you can also put a comment in the Q&A and we can adjust our technical aspects. If you're having any issues, we will be monitoring that. So with that, I'm very happy to introduce our first student, Jillian Epstein from Cornell University, who's going to be talking about searching for the X-ray light from protostars.
Hello, everyone. Thank you so much for coming. As Regina said, I'm Jillian Epstein from Cornell University, and this summer I worked with Dr. Dave Principe from MIT. Today I'm going to be talking to you about searching for the X-ray light from protostars. And this title alone probably brings at least one question to mind, being what are protostars? Well, protostars are simply baby stars. Stars form from large clouds of gas and dust that collapse under their own gravity, forming what we call class 0 protostars. These are small glowing stars surrounded by huge clouds of gas and dust, as you can see, which hides them a bit from view. Over time, this gas and dust will collapse into a disk, forming a class 1 protostar, and eventually this disk will be dissipated, forming a star like we see today for our sun. However, before we get too deep, it is important to know why we care about protostars. Protostars tell us a lot about our own solar system. Solar systems form as the star forms, and as such, understanding star formation is a big part of understanding planet formation. By understanding how stars form, we can understand how our solar system formed and why it has the properties and characteristics it does today. Additionally, of course, understanding star formation can help us understand how our sun forms. And this can really help us understand the past, the future, and the present of the sun and why it behaves the way it does. Most importantly for that would be solar flares. These are of particular interest because of their ability to knock out satellite and communications technologies. They also give us the auroras, and they're very hard to understand and predict. So by understanding how this star forms, we can better understand this solar activity. Flares are also extremely important for this research because they generate X-rays. And when I say X-rays, I do mean the exact same things that machine at the doctor's office uses to take images of the bones in your body. Here we have a solar flare on our sun with the Earth to scale, and it can seem like the plasma the material of the sun is just suspended in space in this random loop, but it's not. It's actually following the complex magnetic fields of the sun to create this gorgeous flare. And on class 0 protostars, the earliest stage of star formation, these flares can be 10 times the size. So they are extremely important and they emit X-rays. And why do we care that they emit X-rays? Well, a piece of our puzzle is missing. This is the same diagram I showed you earlier showing the different stages of star formation, but I added a row saying whether or not this stage of star formation emits X-rays. And as you can see, we have an answer for every stage except class 0. That's a big question mark. So we want to figure out, do class 0 protostars emit X-rays because they have these beautiful solar flares that may do so? But to understand why that's a question that remains unanswered, we have to understand what a protostar looks like on the inside. This is an artist's drawing of a cutaway of a class 0 protostar, and there's a lot going on. In the center here, we have our little glowing protostar. Surrounding it, we have a protostellar disk, just a huge disk of gas and dust orbiting around the star. Coming out of the north and south poles of the star, we have our jets. These are an entire area of research on their own, so unfortunately I am not able to elaborate on them any further. And most importantly for this research, we have this huge black cloud of obscuring dust. This makes the protostar very hard to see and forces us to look in other wavelengths for them. Here I have 3 images of a protostar in the Orion Nebula. This image on the far left is in optical. This is what you'd see if you pointed your telescope in that direction. And you may not believe me that that is a photograph because there's not much there, but it is a photograph. There's just so much dust being vaguely lit by background bright objects, and we can't see anything. So we look in infrared, which you guys may know of as heat. And suddenly the image is beautiful. There's all these stars there. And particularly, I want you to pay attention to this star being pointed to by my golden arrow. This is a class 0 protostar that we are paying attention to. And if we go into X-ray, as I mentioned earlier, you see that some stars disappear, some stars get brighter, but we can still see objects, and the protostar pointed to by my golden arrow is still there. So it appears that this class 0 protostar emits X-ray. Does that mean that class 0 protostars emit X-ray? Well, one example is not enough to make a claim. So we went looking for more. This here is also the Orion constellation. You probably recognize Orion's belt right here. This is that big bright star Betelgeuse. And behind this is the Orion Nebula, with this region kind of being the part you can actually see with the naked eye. And this Orion's Nebula is a huge star-forming region, a ton of newly formed stars over there. And we decided to look at 230 of them. So each one of these are a class 0 protostar that we knew the location of and figured they may emit X-ray. So we went through them and looked for X-rays and found 11. Each of these pink dots is a class 0 protostar that we found to emit X-ray, which is super exciting. That means that a piece of the puzzle is found. We can at least tentatively say, yes, class 0 protostars can emit X-ray. However, what can we do with that information? Well, you guys have probably all used prisms, which you hold up to some sunlight, and then it splits that white sunlight into all its component colors. Well, imagine we had an X-ray prism, which we held up to our star, and it split the X-ray light from our star into all its component colors or wavelengths. If we plotted the X-ray color or wavelength against its brightness, we get this spiky line here. And each of these spikes is called an emission line, which corresponds to a specific chemical that is present in the star. However, unfortunately, X-ray prisms are not little triangles of glass. You need to use one of NASA's great observatories out in space. The particular one is Chandra. And because of the complexities of X-rays, when Chandra is fed this spiky purple data, it will actually return this slightly smoother orange line. But that's okay, we perfectly understand how this works. So when we are given data from Chandra of a particular protostar, which is the gray points in the background here, we can use our from the laboratory understanding of plasma and fit a model to these points. From this model, we can answer a few questions. This includes how obscured is the star? How much gas and dust is hiding this star from our view? What is its composition? What is it made up of? And how hot is it? What is its temperature? And from fits like this, we can learn that class 0 protostars are 10 times more obscure than class 1. And remember, class 1 is that stage where it's just the disk without all the material around it. And these protostars are 30 million to 100 million degrees Fahrenheit, so extremely hot. And because they are so hot, we can actually learn a bit about what their complex magnetic fields that were creating all those flares look like from this information. So if we take a step back, we have found 11 new examples of class 0 protostellar candidates emitting X-rays. And this means that we can at least tentatively say that class 0 protostars do emit X-rays. And by looking at the spectra from these X-rays, we confirm that class 0 candidates are just as hot and just as obscured as theory has predicted. Thank you.
Thank you, Jillian. Do we have questions? And while you're thinking of questions.
Maybe, yeah. Christina had a question.
Okay, so Christina, yes.
So you found 11 of them that emit the X-rays. Do you have any guesses as to why it was 11 and not all of them?
Yeah, so that,
Repeat the question.
oh, yes. So Christina asked, I found 11 that emit X-rays, and why was it only 11, not all of them? And that is a great question. So there's a couple factors in this, and I actually have a couple bonus slides to show you. So this here is an image of the disk around a protostar, an actual image of a disk around a protostar, and you can notice it's an ellipse. It's not a circle, but we assume the disks are a circle. So that means that this disk is at an angle to us because we're only seeing ellipse. And as I showed over here, we have jets coming out of the north and south, and then we have this disk. So, sorry, I need my hands. If the disk is lined up like this, the X-rays need to go through all that disk material, which blocks it, so we don't see it as much. If the disk is lined up like this, the X-ray needs to go through all this jet material, which blocks it, so we don't see it as much. So there's a kind of a sweet spot, which filters out some of them. And then on top of that, Chandra has not looked everywhere in the sky. Actually, it's a bit of a confusing map, but everywhere there's a circle and it's not gray is someplace Chandra has looked, which is a lot of places, but there's a lot of gray space too. And unfortunately, some of our stars fall in that gray space. So that factor, basically, some of these stars have not been observed with Chandra, have not been observed long enough for it to show up. You'd need to, look at it for days, and we did not do that. So those two factors together kind of filter out a bunch of the ones. So we basically got the brightest ones that were just right.
We do have an online, oh yeah, go ahead, yeah.
For the life of the stars from the gas cloud, is that obviously long period of time, but is it a slow transition? Or are there periods of sudden change, like suddenly the gas cloud collapses?
On human timescales, there is no sudden change, but some of these phases do occur faster than others. And it can depend a lot actually on the mass of the star. Big stars go quickly in the scale of astronomy. Astronomy is kind of like geology, nothing happens fast. And small stars would go much slowly, much slower, and a big star could go through its whole life before a small star finishes forming. But not, if we look at it for our whole life, we're not going to see anything.
So class 0 is like class 0. There's like early class 0 and later class 0. Maybe more days.
Not my area of knowledge. Yes.
Why is it important to find out if they emit X-rays or not?
Yes, so X-rays are very heavily connected to what's going on inside the star. They're just a way we see it. You know how Earth has its magnetic field? Well, the sun has a much more complex magnetic field, and that's a big part of those flares and stuff that knock out satellites, knock out communications technology. So by understanding these X-rays, we can learn about that magnetic field, which can help us better understand how not to have our satellites knocked out.
We do have one question online, which is, what techniques and tools did you use to look for and evaluate the potential sources you evaluated?
Yes, so I'm actually going to go back to our map of Orion. So this collection of stars right here, all the class 0 ones, we looked at, someone else listed where they all were. So we took that list and then we went looking at images of X-ray and said, okay, we know there's a star here. We can see it in the infrared. Is there an X-ray there? And we could eliminate some of the 230 with computers saying, oh, do I think there maybe could be? And then I went through and said, that's a false positive, that looks spot on, that's a false positive, that looks spot on. So a mix of a little computer help and a lot of looking at images of X-rays.
Okay, great.
Right, I'll be nice and get you to the end of these.
Cool. Sorry we have a little technical thing because I realized I couldn't see the Q&A, but for everybody in Zoom, we can see the Q&A now. So if you do have questions, feel free to put them in the Zoom and we will be checking them. And if we don't see it right away, we will get to it as soon as we can. All right. So now I'm really happy to introduce our next student, Sophia Chan Davis, who's going to be talking about shining the X-ray light on planetary nebula in globular clusters.
Yeah, well, hi you guys, my name is Sophia. I'm very excited to share my summer's worth of research with you all today. Working with Dr. Rudy Montes at the Center for Astrophysics, we shined the X-ray light on planetary nebulae and globular clusters. And I know that was a mouthful, but don't worry, we're going to break it all down. So to start, we need to understand what a planetary nebula is. So I know their name is a bit misleading, but actually planetary nebula have nothing to do with planets. The early astronomers that first observed these objects looked through their telescopes and saw these kind of round, faint, disc-like shapes that resembled planets like Jupiter or Saturn. The observations that they were using with the particular instruments, these instruments were very crude by today's standards and were unable to resolve the intricate details that you see in these pictures today. It wasn't until much later, with improvements in technology for telescopes and a better understanding of stellar evolution, that we were able to soon realize that these are not planets at all. Instead, planetary nebula are the late stages of dying stars. If you take a star similar in size to our very own sun, when that star runs out of fuel, it can no longer support itself against gravity. And so in turn, the outer layers of the star are expelled out into space, leaving a shell of gas and dust. What's left behind is the core of the star, a hot and dense white dwarf, and that emits ultraviolet light. That light then energizes the surrounding gas and dust, making it glow in all the beautiful colors that you see here. But one thing I want you guys to notice is look at all these different shapes. So clearly, planetary nebulae come in all sorts of shapes and colors. And one thing you might be wondering is, how exactly does that even happen? Well, if you're thinking that it's a single star's doing, you would be right alongside thousands of scientists who thought the same thing for decades. It wasn't until recently, though, about 2009, when scientists began accruing evidence that this may not be the result of a single star. In reality, planetary nebulae are more than likely influenced by two stars, a binary system. A binary star is when you have two stars that are gravitationally bound to one another, and they orbit the common center of mass. Binary interactions between stars can create the complex and beautiful dynamic shapes that you see in all of these images I've shown you today. Binarity also introduces X-rays, which we've heard a little bit about already. So what we must do then is, before we decide why that's even important, let's talk about globular clusters. So globular clusters are dense groups of ancient stars. And as of today, there are only 4 known planetary nebulae found in these globular clusters, which is presented to be quite a stellar mystery for scientists. And located in this globular cluster M15, K648 is one of the few known planetary nebulae to be found in a globular cluster. And this is interesting because M15 stars are ancient, but the presence of K648 indicates a very recent stellar death. And so this raises questions as to why this star would be reaching this stage in its life in a population that is already so old and past that. One possibility, though, is that the star that formed K648 is actually part of a binary system. Remember that binary interactions can alter the evolution of stars, potentially delaying its planetary nebula phase. But how do we even prove that or determine that and all of that? So remember earlier, I said that binary stars can emit X-rays. And so we have to go looking for those, which is what I've spent the past 10 weeks doing. But what are X-rays? So X-rays are just another form of light that is just invisible to our eyes. And we can look to the electromagnetic spectrum to understand that. So the electromagnetic spectrum is just the range of all types of light. And if we go down to radio waves, the longest wavelengths, and down to gamma rays, the shortest wavelength, we can see that everything in the middle, from microwave and infrared, all things that we cannot see. But one thing you may notice is that visible light actually makes up a very small portion of what we are able to see. Another thing you might notice is that if we move down to radio waves, where we have the longest wavelengths, we actually have the least energy. When you move closer towards gamma rays, which is the shortest wavelength, we actually have the highest energy. Now, this is a very, very important notion in understanding how exactly X-rays work and how they're useful to us. So, X-rays have shorter wavelengths, but higher energy than visible light. And so that allows them to penetrate into various materials. If we think about the most common use for X-rays, like medical imaging, X-rays are able to go through human tissue, but get absorbed by denser materials like your bones and metal, which makes them great for creating images for the insides of objects. Fortunately for us, though, X-rays are kind of dangerous, and our Earth's atmosphere absorbs all those. So you will never see an X-ray telescope down here on Earth. So to produce X-ray images and find X-rays in space, we look to NASA's great observatory, Chandra. And so we take images from Chandra and images from the Hubble Space Telescope to create a composite image of K648. Now, a composite image is a layering of images together. Imagine if you take pictures of the same scene, but each picture reveals a different detail of what you're looking at. When you put all of those photos together, you get a complete picture of everything that's going on. Now, in astronomy, we do something very similar, but instead we use different pictures from different telescopes with different light, like X-rays and visible, to create a picture of the objects that we're studying so we can fully understand everything physically that's going on. So that's what I just did. So here we have a Hubble image in the optical of K648. The red indicates the presence of hydrogen. Now we have another picture of K648 using Hubble, where the green indicates the presence of oxygen. And now this is an image of what K648 would be if you were to go out in space and look at it yourself with your own eyes. But we have one piece of the puzzle missing, and that would be the X-ray emissions that K648 has. And so this was taken by the Chandra X-ray Space Observatory. Now, creating a composite image is not easy. It takes a lot of painstaking alignment. If you imagine a jigsaw puzzle, but you have several jigsaw puzzles of the same picture, and they're all different colors, in order to get your picture correctly, you have to align all of those puzzles on top of each other perfectly. And then that is what allows us to create our composite image. And so here we have K648 in its full glory with its optical and X-ray components. And one thing I do want you to notice is the location of the X-ray emission we found in K648. As we can kind of see, it is located in the northern arc of the Planetary Nebula. Now, this is very important because we've ended up proving that the X-ray emission originates from the northern arc of K648 and not the central region. If we found the implications for this, if we found the X-ray, which is denoted in blue, to be in the center, that would imply that this was created by a central binary. And since we did not find that, and it was located in the northern arc, we can confirm that the X-ray emission is more so likely related to shocks due to its location in the northern part. And so binarity is neither proven nor disproven in this particular case, but more research would be needed in order to figure out the binary component of K648. For the most part, this stellar mystery has been solved. And I am happy to take any questions.
Great, thank you, Sophia. We're gonna open it up to questions now and also questions on Zoom. I can see the Q&A now, so if you have any, go ahead and type them in. And if anybody in the room has any questions, please feel free. Yeah.
This is going to be really basic, but you referred to a north and south in both the presentations. Is that a universal orientation in space?
Actually, it's not. So it's what's interesting about this picture and with most, or actually all space observations, north is up in this sense, but not in the traditional sense that we think of east. East is actually pointing this way in our space observations, which is kind of interesting to think about. But you kind of have to like orient yourself like you're facing up in the sky, and that way you can get a better sense of how we think of like north and east. But that's a product of how we view objects in space. So
So is it a uniform thing across all of space?
yes.
Okay.
Yes, it is. Which it's weird. It's really weird. But yeah, north, east, south, west.
Yes, if you think of the sky, like think of like a globe, and instead of a globe, think of a globe of the sky, right out there. And so just like on a globe, you could have a north, west, and east, you could have the same on the sky. So it's the way that we view it, and then we can assign a north, south, east, yeah.
So is there a difference in location with the X-rays in, like in planetary nebula in globular clusters versus out of globular clusters? Or are they all usually found in the north region?
Right. So first, finding a planetary nebula in a globular cluster is really weird because all the stars in a globular cluster are super, super old, close to the age of our own Milky Way. So if any of those were to have gone planetary nebula, they would have already done so and have disappeared. So the fact that we're seeing one so recently is a mystery in itself. The X-ray emissions found in planetary nebula are dependent on the physical mechanism that created them. So if it was a binary interaction, we would expect to see that blue here in the middle. But if it's in any other location, such as how we saw here in the northern arc, those are created by shocks or just the gas being expelled super fast, similar in the way that a supersonic jet kind of works, just with gas in space. So the location of X-rays can tell us physically what's going on. Yeah.
Is there a scale on that photo? Like the shocks were seen like X light years away from the.
And we'll just repeat the question for online, I forgot.
Oh,
before.
yes.
How big is that?
All right, so the question was, what is the physical extent of this planetary nebula? Now, I don't know the physical extent of this particular one, but typically whenever the nebulosity or just the gas you're seeing expands, you're looking at something that is about 2 light years across. And to kind of ground us in what that unit means, that's just the distance light takes to travel in 1 year. The light from our sun takes 8 minutes to reach us during the daytime, so 2 light years across is pretty dang big.
Let's see, we have a question online. Great presentation, Sophia. I have a small question. If the binary nebula theory is true, what would be the differences in our understanding of how these nebula interact with the universe versus our current understanding, aka one star system?
Right. So if we look at the current evolutionary model of planetary nebula, and remember, we can look to our sun as one of these stars that can go planetary nebula. So there's lots of weird words on here, but for the most part, how we understand planetary nebula to be formed is the star lives on its main part of its life for about 11 billion years, which is a really long time. And then it moves to a red giant, which just means now it's burning a different type of gas in its core. And then we spend kind of this time here where it's doing some pulsing. So it's kind of losing parts of its gas. It's starting to run out of fuel. And then after that phase kind of ends, that's where we enter into the planetary nebula phase. But currently, under stellar evolution, we think this only takes one star. If this binary hypothesis gets proven, there's a different sort of model as to why they're formed. That's not to rule out the single star. The single star actually is what probably makes the spherical shapes. What the binary hypothesis would help us understand is why we get all of these weird asymmetries and different jet-like structures. And essentially, all you kind of need to take away from this is if we have a second star in the mix, that's what would kickstart the planetary nebula phase. So not a complete change in stellar evolution theory. One thing I will say is if the binary hypothesis is true, we would not expect our own sun to go into a planetary nebula, which is, I think, the biggest implication for us. Not that we'll be alive by then, but yeah.
Awesome. Okay, if there's no more questions, let's. Oh. And next up, we actually have Naija, who is joining us online. So one of our interns, Naija, is a Division I soccer player. Soccer practice started already. And so she actually had to go back to her university. So she last week, but was continuing to work with us. And so she's going to be joining us online to give her presentation. And let me just see if I can make sure. 1 second, Naija, let me bring up your video here so we can see you in the room. All right. And I think if I actually put it on, go ahead and unmute yourself, Naija, and then I'm gonna make sure that we can only see you once you start talking. Okay. Perfect. Okay. Okay, great. So this is Naija Bruckner, who's at Rice University, and she's going to be telling us about how windy is outer space.
All right. Hi, everybody. My name is Naija. I've been studying wind in outer space, as Regina just mentioned. But specifically in outer space, I'm interested in galaxies. So let me see if I have, perfect. Okay, so a galaxy is just a collection of gas, stars, and dust that's held together by gravity. And on the left, we have a picture taken by a telescope that we've built of a galaxy. And as you can see, it's pretty bright. That's because there's so much gas and so many stars clustered up there. I'm not actually using a telescope to study the galaxies, though. I'm using simulations. And simulations are essentially when we try to use a computer to mimic the laws of physics. So we program what we know about physics and let the computer run a bunch of code and then see if what it produces is similar to what we actually would see when observing. And so in this case, you can see on the right, there's a picture of the simulated galaxy that I've been studying. And it has a pretty similar structure to the actual galaxy on the left. But just to discuss it a little bit more, this is the one I was looking at and studying. It's about 100,000 light years across, a little more than that. And I think Sophia mentioned it, but a light year is just how far light can travel in 1 year. And actually our Milky Way galaxy is about the same size. It's around 100,000 light years across. Now you'll notice on the right side of this plot, there's also a color bar indicating the density. So the regions that are more yellow and green are higher densities of gas, and the darker red and purple are less dense. So we notice that there's still a lot of gas and stuff kind of in the middle of the galaxy, similar to the picture we have. But both of these are just pictures of the galaxies themselves. But galaxies change over time and they interact with their surroundings. And so to fully get a better picture of what's going on, we need to study the areas around them. And so that means we study the circumgalactic medium. The circumgalactic medium is really the gas that exists outside of galaxies, but is still gravitationally held in. And for kind of a scale reference, this cartoon depicts a galaxy right at the center, but then the whole surrounding regions are part of the circumgalactic medium. So there's a lot of gas that's really considered to be interacting with the galaxies. And it's important to understand what's going on in the circumgalactic medium because it can help us understand how galaxies form and evolve. And really, when we look at the arrows in this diagram, that makes a bit more sense, right? There's a lot of arrows traveling into the galaxy, and that's the material that's ultimately going to feed the galaxy as it grows and changes over time. But we're also interested, for example, in the gas coming out of galaxies. So that's marked as outflows on this diagram. And that's interesting because it can actually tell us about star formation within the galaxy itself. Now, my presentation title was about wind in outer space. And so I'm specifically interested in what we call turbulence, especially in these regions of gas coming into and out of the galaxy. And turbulence, just like on an airplane, it's essentially how rough and chaotic the wind is. So if you're traveling on an airplane and there's a bunch of wind pushing you in the same direction at the same speed, it's going to be a really smooth ride. And so that's not very turbulent. But if you have a bunch of different pockets of wind pushing you in different directions, that would be higher turbulence. And so I'm interested in looking at the turbulence of the gas around galaxies, so that we can study what kind of gas is moving into and out of them. Now, the thing about the circumgalactic medium is that it's really faint. It's almost invisible. So the galaxy is bright and we can take pictures like the ones I showed on the previous slide, but the circumgalactic medium is so faint that we can't really observe it directly. And the way we do that instead is by using a couple tricks. So this diagram kind of explains how that works, but first, let me give an analogy. So imagine you have a flashlight shining white light, and then you put like a red film on the front. Well, the light you get out is going to be red. And so you know that light has changed because it passed through the red film. Well, similarly, we can use kind of these background astronomical objects that emit light where we know what kind of light should be coming out. And if that light passes through a circumgalactic medium on its way to Earth, it changes. And so when that light gets to Earth, we can study how it's different than what we were expecting. And that tells us about the actual gas in the circumgalactic medium. Now let me talk about this a little more. So first, let's imagine that light just goes straight from the distant object to the observer on Earth. It doesn't pass through anything. That's case one. And then case two is when it does pass through something like a circumgalactic medium, here that's indicated in purple, and then changes before reaching Earth. So if we put up a prism to the light in the first case, we would see the full rainbow. You'd get all the colors. It would be exactly like what you expect. But in case two, if you put up a prism, you get something where some of the colors are missing because that gas that it passed through has actually absorbed some of the colors or prevented them from getting all the way to Earth. And when we study which colors it is that are missing, we can understand what kind of gas was in between us and the original object. Now, because I'm using simulations, I can kind of choose to put my light rays wherever I want. And so here I have a diagram of two different light rays that I've added near our galaxy. And we can mimic an observation by letting, essentially the computer will let light run through this galaxy. And then at the end, we'll see what an observer would see if there was some sort of astronomical object here and we were at the other end of the arrow. So in this diagram, there's two rays of light. The one on the left clips basically the edge of the galaxy, whereas the one on the right just passes through more diffuse gas. And so the colors that we would see at the end of each one are different. The first one might have a lot more missing colors because it's passing through more gas, for example. And so what I was doing this summer was plotting a lot of these rays and then seeing what I would be able to tell if I were just an observer and I didn't have all the simulation data. So specifically, I was interested in understanding, can we determine turbulence from something observable? Just to recap, turbulence, again, is how chaotic the wind is. Think of an airplane ride being really bumpy. And that's something I can calculate within the simulation, but we can't directly see from Earth. Now, the observable quantities is kind of what I was showing you with the colors getting blocked. And I want to tell, is there something about which colors get blocked or along those lines that indicates how turbulent it is in the gas that the light passed through? And so what I did was I plotted the simulated turbulence against the observed turbulence. Now, if there were a perfect relationship between the two, where what's happening in the galaxy is exactly what you see, all the points would fall along this blue dashed line. Clearly, that's not the case. First of all, there's blue dots and red dots. So the red dots trace colder gas, and the blue dots trace hotter gas. And one note before I discuss the rest of this is that you can see there's a bunch of points kind of lined up along the parallel to the y-axis. Those aren't points we're interested in because we're interested in where there is turbulence, and those points essentially represent places where we didn't measure any turbulence. Now, what we found is that it turns out hot gas is a better tracer of turbulence than cold gas is. And ultimately, this is really important to figure out because what we eventually want to do is figure out what we're observing in real life, not in simulations. And so with this, I can go tell observers, when you want to study the gas flowing into and out of galaxies, you should be looking at hot gas to study how it's moving instead of cold gas. Okay, so to recap, I'm interested in galaxies. But to understand galaxies, you need to understand the circumgalactic medium, or the stuff around galaxies, because that's moving into the galaxy, it's moving out of the galaxy, and it really impacts how it grows and changes over time. What I found was that we should be looking at hot gas to measure turbulence in the circumgalactic medium. And ultimately, this is useful because it means that we can go tell observers how to interpret their results. And that's what simulations are the most beneficial for. They can help us interpret the real world observations that we don't understand everything about yet. And with that, thank you. Are there any questions?
Great job, Naija. I'll open it up to questions. If anybody in the room has any questions about turbulence. Yeah, Christina, I'll repeat so yeah, everyone can hear.
I don't know if this is a stupid question or not. So like when you're talking about like the hot gases and the cold gases, are there like types of gases that tend to be hotter or colder, or is it just any gas and then whatever physics is applying to it is making it hotter or colder?
Yeah, so the question is, Naija, I don't know if you could hear that, but I'll repeat it. The question is, when you're talking about the hot and the cold gas, are there different types of gas that are associated with the hot versus the cold, or is it sort of all the same gas and just some of it's hot, some of it's cold?
That's a great question, Christina. So actually, what I was looking at were two different types of gas that I renamed hot gas and cold gas to make it simpler to see. But hot gas tends to be particles that are more energetic. And so, let's see. So atoms can, when they heat up, can lose electrons and get what we call more ionized. And so the higher the ionization state and the more energy an atom has, the hotter the gas is going to be. So in this case, the hot gas I was looking at is actually oxygen 6, which is a highly ionized gas. Whereas the cold gas is carbon-2, which is a low ionized gas. So yeah, it has a lot to do with the type of gas. And that was actually more directly what we were tracking than the temperature itself. So great question.
Other questions while I check if there's anything on the Zoom. If anybody in the Zoom has questions, go ahead and pop them in the Q&A. I'll ask one question. Naija, do you want to talk a little bit more about some of the advantages or disadvantages of simulations versus observations?
Yeah, so the great thing about simulations is that there's so much information, you know everything you need to. And that meant that I could look at it both having all the information and just as an observer and kind of see where those things might line up. The disadvantage is that we don't know all the physics that's going on, and it takes a long time to run the code for these simulations. So first of all, we don't know, this is a good estimation maybe of some parts of galaxies, but if we knew all the physics and could perfectly replicate the universe we have, then we wouldn't need to be studying anything because we'd already know everything. So it's kind of a feedback loop. Simulations aren't perfect because we don't know all the physics, but we see whether they can replicate things like galaxies in a way that's similar to what we observe. And then if there's things that are off, maybe we go back and update the physics that we put into the code. So They're great because they can help us study what we can't directly see from Earth and see how things might work based on our understanding of physics. But because we don't perfectly understand all of physics, there's still things that are off and don't reflect the actual universe.
Great. Let's see. I don't think there's any other questions in the Q&A. And if there's nothing else in the room, let's thank Naija again. Thank you so much. And I think next we have Gada Tafara, and I'm gonna adjust. I think it's here. Let me just close. Oops. This quick technical. Oops. Showing your slides early. Sorry about that. Sorry, everybody. This is Gada Tafara from Pomona College, and he's going to be telling us about his project studying the evolution of gas in the early universe.
Okay, yeah. So hello, everyone. Thank you for coming. Like Regina said, my name is Gada Tafara. I am a rising junior at Pomona College. And this summer, I worked with Dr. Regina Jorgensen here at Mariah Mitchell to study the evolution of gas in the early universe. So for some background, it's important to understand the composition of the universe. 95% of the universe is dark matter and dark energy, which I won't be getting into in this presentation, but we know it exists. The other 5% is atoms. So that's everything that you've ever known, ever seen. It's the planet, it's you, it's the sun, it's everything. But in context of space, these atoms can be broken down into gas and dust. I'm focused on gas, and in the next presentation, Fiona will talk about dust. So when I say gas, what do I mean? In context of my summer research, I'm focused mostly on hydrogen because it makes up most of the gas that's in the universe. So with that being said, it's important to know that gas and dust are the fundamental building blocks of stars. So when you get a gas cloud that is large enough, about 80 times the mass of Jupiter or more, it will collapse inward over time under the force of gravity, and you will get a star. But if you have a larger gas cloud, kind of on the range of a few trillion to 1 quadrillion masses of Jupiter, you can collapse under the force of gravity and you would get a galaxy. So we know that galaxies are structured by gas and stars are structured by gas, and galaxies are made of stars. So we know that galaxies contain a lot of gas. This is an image of a nearby galaxy. And because it's so nearby, you're able to see not only the colorful hot gas in the center, but also the gas that surrounds the galaxy. If it was any farther away, we wouldn't be able to see this distinct detail. And so if we zoom out to a cluster of galaxies, this is an image taken by Hubble, you can see that between these galaxies, it looks like there's nothing. If I show this to you, it would be easy to intuitively say that there's nothing there. But we know that diffuse gas is there. In fact, a significant amount of the gas that makes up the universe exists between galaxies. But let's zoom out once more. This is a simulation called the cosmic web, or the image is called the cosmic web. And this is the most zoomed out view that we're able to get of the universe. We can't observe this here from Earth, but you'll see that this web is created by these purple filaments. So after the Big Bang, matter was uniformly dispersed, but over time, gravity caused these filaments to form. And these filaments, while they're hundreds of millions of light years long, they are full of diffuse gas, which means it's not dense, and that means that it's very cold and doesn't emit its own light. So how did I observe gas? Well, I looked at this mysterious kind of gas. It lies in the middle ground between the cosmic web, full of diffuse gas that we can't really see, and galaxies, which we know doesn't tell us the full story of how gas evolved over the universe. And so this middle ground is called a sub-damped Lyman alpha system, or a sub-DLA. I won't get into why it's called that, but from now on, whenever I say sub-DLA, I am referring to this middle ground. So why did I say that there's nothing significant? Well, to observe a sub-DLA, we have to look at a bright object behind it. But when we get this light from a bright object, we can only see the parts of gas, or the parts of light where gas has absorbed the light. And so sub-DLAs have a certain density and they're in this middle ground, but we don't know if they're a gas from galaxies or distinct gas clouds that are found in the cosmic web. But as light travels towards us, every gas cloud that comes in between us and the object will be disrupted. And so there's this spectrum that is created from the light that is observed. And so for the purposes of this project, the bright objects we were looking at were galaxy centers. And so there's a peak where the gas or the light emits, and every time a gas cloud is shown through, there is a dip in the graph. And so each one of these dips is called an absorption. And every time there is a dip, we know that there's gas there. And so we can study the wavelength of the light that is absorbed to understand how far away the sub-DLA is. And also how big the absorption is tells us how much gas is in the cloud. And so what did we do with this? Well, that's not that simple. That was a cartoon demonstration of a spectrum. And this is more of what a real spectrum would look like. You have your bright source of light, and it has to travel through that cosmic web that we talked about. And every time light travels through the cosmic web, tiny bits and pieces of light are absorbed by the cosmic web. And that makes it really difficult for us to observe. And because of that, there is a distinct point where astronomers have stopped observing sub-DLAs. And because of that, there is a large gap from the beginning of the universe where we don't know how sub-DLAs or gas as a whole has evolved. And so with this project, I sought to change that. So there was this data set taken from the Keck telescope in Hawaii, and it had 727 light spectrums taken in it. And it was important to get this specific sample because it contained a lot of far away, distant bright objects. And so we refined this data set to optimize our search for gas based on distance, the resolution of the light spectrum, and the quality of every observation. And with that, we got it all the way down to 141 spectra. And so I went through every single spectrum one by one and looked for these distinct dips in the graph. And so you can see the cosmic web absorbing tiny bits and pieces of light to the left of the brown square, but there's this large absorption that you can't really miss. And so that's what I looked for in every single one. And so by eye, I found 550 absorbers in the sample. And with this, I'm able to calculate the density of the gas in these sub-DLAs and calculate how much gas has evolved over time. And why does this matter? Well, like I said before, gas creates galaxies. And it's a fundamental part of the universe to understand galaxy formation and evolution. And sub-DLAs are a very important piece of the puzzle that we don't yet understand because we haven't studied them yet. Thank you.
Great job. All right. Questions about gas? Yes.
Great job, that was awesome. When you say you look at wavelengths, are you actually observing it, or is that something a computer is doing? Or is it really by eye?
Let's repeat the question.
Oh yeah, so the question was, do we look specifically at the wavelengths, or is it something the computer does? So are you talking about this image?
Yeah.
So yeah, I went through all of them by eye and looked for them individually.
That's crazy.
Christina?
So like right at the end, you said, so you were able to like see the density of the gas and then like a general amount of it. Are you able to use that information to try to figure out like what kind of gas it is? Or is there not really enough data to help with that?
Yeah, so the question was, we're able to like calculate the density and the amount of gas in these absorbers. And is that something that's, what was the question?
Like can you can you use that to identify like what kind of gas it is or no?
Okay, yeah, the question was based on the density, can we like determine like what the gas is? Not really. We know that it's mainly hydrogen.
And I'll just say, if anybody in Zoom world has questions, please go ahead and put them in the Q&A. See any yet? So there's time for more questions in this room.
Are there any features in these spectra that would produce false positives? So they would look like that, but they're actually from something else?
Yeah, so the question was asking about if there are any false positives. There is a chance, but we filtered the spectra based on like the error that was in the observation. So ideally, we have already filtered out all of the potential false positives.
So, the study of moving like back, what is it the rate at which the research people, and like when do they think that they'll get back to the beginning of the universe and how the full started?
So the question was, when will surveys get towards the end of the universe? That isn't really the issue. The issue is that as time like progresses, or like the distance between us and like the beginning of the universe, or like where bright objects are, there's more cosmic web that the light has to travel through. So like finding these bright objects and finding sub-DLAs that are between us and the bright objects gets like way more difficult. No, there's this there's this like scientifically proven like point at which you can't really observe them. It's called the Gunn-Peterson trough. I won't get into that because that's like a really long thing, but you just like can't get past that point because there's too much cosmic web.
I'm gonna need to try to frame my question, but you did such a great job explaining everything, but I just don't know a ton about astronomy. How do you know that you're looking at like the early universe instead of like stuff that's happening? If that makes sense.
Yeah, so the question was, how do you know that you're looking at the early universe? Basically, there's this term called redshift, which just associates like the age of something to its distance. So we can just look at the redshift and we know like when it is in the universe.
And we actually have a follow-up question online from Maddie, who was a REU intern here last summer. To follow on that question, Maddie's asking, just a technical follow-up is, what is the redshift range of your sample spectra?
Oh, yeah, it is 2.2 to 5.6.
So for technical folks, that's helpful. And then there was one other question that I think you sort of answered already, which is, can other things besides sub-DLAs cause dips in the absorption graphs?
Yes, there are things that are more dense, but they are closely related to galaxies.
Awesome. Well, if there are no other questions, let's thank Gada again. Okay. And our next speaker is Fiona Lopez from Texas A&M University, who's going to be talking about dust origins, exploring the secrets of early galaxies. And you may notice we are moving in progression from nearby things to the farthest away things. That's how we organize the talk order. So we're getting farther and farther away now. So thank you, Fiona.
Yeah, as mentioned, my name is Fiona Lopez and I am from Texas A&M University, and this summer I have been working with Dr. Monica Relaño from the University of Granada in Spain, and my research focuses on exploring the secrets of these early galaxies and their dust origins. Now, to begin with, I am going to explain what exactly these early galaxies are. Now, these early galaxies are the first galaxies that formed when the universe was very young. Their light takes billions of years to reach us, and this has deemed them to be called distant galaxies. Now, the image on the right here is an image taken of deep space by NASA's James Webb Space Telescope, or JWST. Now, there is a lot going on in this image, but I'm going to have you guys focus on the areas in orange here, which represent the early galaxies that I've been talking about. And these galaxies were formed when the universe first began. And feel free to ask later more about this image, because there really is a lot going on in it. I know. So what I'm trying to focus on is understanding how these early galaxies behave in comparison to the nearby galaxies that we are more familiar with. We know for a galaxy that it is made of three main components. The first component is stars, which you are probably most familiar with. And the second component is gas, which you heard a lot about and learned from Gada in the previous talk. And the third component is the unsung hero of galaxies, known as dust. Now, the dust in galaxies I'm referring to is the same dust that makes up the dust bunnies under your bed. Dust is made of tiny bits of sand or soot, and dust is approximately 1 micron or 1/1,000,000th of a meter. And for scale, the width of a hair strand is approximately 100 microns in size. Now, dust is made out of carbon, oxygen, iron, and other similar elements like that.
The image on the right here are some microscopic views of dust grains taken from an ancient meteorite that landed on Earth. And you can see this white bar for scale. This is like 2 microns, for example, just to show you some scale of the size of the dust grains that we are looking at. Now, this cosmic dust has 2 main effects. Just how fog can make objects in the distance hard to see, dust can cause objects to be dimmer or sometimes completely hidden from view. Dust grains block and scatter the starlight that we'd receive. In this image over here, you can see these areas in black, and this represents the dust in the galaxy that we're looking at. And there's some light peeking out, but we can see a lot of the light of stars is hidden completely by the dust in this object. Now, while dust may make objects appear murky, it is also essential to star formation. You heard before about how stars form. The gas cools down and collapses to form stars. Dust is essential for that cooling process of the gas. So when looking at galaxies, we want to look at regions where the dust is to understand more about star formation and where it occurs in essence. So I'm going to be talking about how dust in galaxies emit infrared light. Now, before I get into that, I'm going to explain the images you're looking at here. On the left here is the edge-on of a spiral galaxy. So normally you would see a spiral galaxy with all of its arms, but instead we are kind of flipping that and look at the side profile and edge-on of that galaxy. So it looks something like this. Now, this is looking at the galaxy through visible light. And then on the right here is looking at that same galaxy, looking through it in infrared light. And all of these regions in red here represent the dust in that galaxy. So we can look at these regions to understand where the stars are forming and more about the galaxy using infrared light. And to talk more about infrared light, it is not visible to our naked eye. It needs powerful telescopes to look at it. And some examples of infrared light you're probably familiar with are sun's heat from our body, and you might be familiar with night vision goggles and how those have like bodily heat that you can see on them. Now, one powerful telescope to look at infrared light or look at early galaxies is the NASA's JWST, which I previously mentioned. This powerful telescope was designed specifically to look at infrared light, and it's a space telescope. And the reason it is located in space is because space provides a cool, stable environment, which is necessary for these faint and sensitive infrared observations. Additionally, it is located in space because it can avoid the interference that it would otherwise receive from Earth's atmosphere that would block and distort the signal that we'd want to receive. Now, another telescope to look at early galaxies is what's known as the Atacama Large Millimeter Array, or known as ALMA. This is a ground telescope located in Chile. And this telescope was designed specifically to look at radio waves. Now, before I mentioned how dust emits infrared light, well, that was referring to the warmer dust. The cooler dust and gas emits what's known as radio waves that we can look at using telescopes such as ALMA. So ALMA is able to look at these radio waves of early galaxies and understand their composition and structure better. Now, ALMA is located in Chile because it has a dry, high-altitude desert that allows it to have less moisture, as that moisture would otherwise distort or interfere with the signal that we want to receive. Now, my research focuses on observational data from both ALMA and JWST. I have been working with brand new data from JWST to look at a sample of early galaxies. Now, the galaxies I received are in a format known as a data cube. This is a 3-dimensional view of a galaxy, in essence. So it has an X and Y axis, and at any position, we can extract the spectrum to look at the galaxy. Now, this is kind of a slice or an extracted spectrum that I did for one galaxy. Now, this gas we're looking at here is the hot gas that is heated by the stars in its galaxy. And for scale, we can see the white bar here. This shows that the galaxy is over 30,000 light years across in size. Now, for this galaxy, to understand more about the gas and dust distribution, I overlapped maps provided by the telescope ALMA. So in white here is more about the distribution of the gas. Now, before I get into that, I'm going to explain how these contours work. So you might be familiar with a topographical map of a mountain where we have those white lines, and there's a little circle here, and that would normally represent the peak of the mountain that we're looking at. The same goes for this. This is the peak of the amount of gas in that galaxy. So we expect most of the gas to be located in this area of the galaxy. And this gas is what's known as ionized carbon. Now, the important thing about that gas is that it's a known tracer for star formation. So that means that we expect most of the stars to form in this area of the galaxy instead. So to look more into this, we can actually use another distribution that I used, which is the dust distribution of the galaxy, using ALMA information as well. So the dust distribution is overlapped in blue here. And as you can tell, towards the outer areas, it's different in shape. But as we get towards the center, we can see that the blue circle actually overlaps a bit with the white circle. So this means the dust distribution overlaps with the gas distribution when it comes to the peak of the amounts. And since that both of these basically trace the star formation, that means that this shows that this is where we expect most of the stars to be formed in this galaxy. And this is where we want to look at to know that, oh, both of these distributions trace each other and confirm this in a sense. And what's interesting about this is we actually we didn't expect that these early galaxies would behave so similarly to our nearby galaxies. So it's quite surprising that this is a fact. And we're still trying to learn more about this, and I'm doing a lot more data analysis to verify these findings in a sense. So big picture, and here are the takeaways that I would like you guys to have from my talk. Firstly, that early galaxies formed shortly after the universe began, and that dust plays an essential role in star formation. And lastly, from my research, the initial results show that new JWST data appears to confirm that these early galaxies behave similarly to nearby galaxies in a sense. But yeah, that is it. Thank you guys so much for listening.
Questions on early galaxies?
Yes.
Yes.
It's more of a clarifying question,
Yes.
but you're able to see dust around the galaxy because it absorbs all the heat from the gas.
In a sense, it's because it does absorb the heat in a sense.
Okay. So another question, is there ever like so much dust that it like cools the star down too much? Or the galaxy too much?
I'm not sure about that. I feel like it wouldn't cool it down too much in a sense. Like sometimes there is cooler gas that would affect it, but I don't know if it'd be too much in a sense. I feel like I don't know how to answer that very well. Yes.
In the chart that you had with like the white and blue lines,
Yes.
so like in the parts that they intersect, that's not like those center bits, are those stars forming too because there's dust and gas, or?
Not exactly. It's more as if there'd be stars forming, but not like the peak amount of stars forming, I would say, like the most amount. It's funny because in this galaxy, there's actually technically two areas where we expect stars to form, but this is the bigger area in a sense that we're looking at and expect most of the stars to form.
And repeat the question.
Oh,
Sorry,
yeah. I forgot completely, yeah. Yes. Or like the, oh, you mean this one?
That one.
Yeah.
You said that like sometimes like stars will form in the dust. If they form like kind of on this plane, will they have to like move into that? Like, do they ever form like far enough away that they have to like move into the galaxy, or is it they just form like in the dust, like right next to the galaxy, like in the edges? Do stars ever form?
Oh, you mean like if they would form like around here exactly instead of like outsidings?
They like ever form the outside edge of that dust, or are they only right here?
They don't exactly necessarily have to be right near the galaxy. If anything, it's just because it's easier for us to detect it, I would say, because of the infrared light they emit. That's why we're able to see it better. But it doesn't necessarily mean that. It just might not mean they're stronger, I would say, and we can technically like see them as well. I still didn't repeat it. It was I was still trying to. Yes. Or
Who did you call on first?
oh, you can go first.
So we know if we see something that's really, really, really far away, we know it's really old. So there's a relationship, I guess, between distance and time. Like
Yes.
older things are farther away. Are there old things that are nearby?
Not necessarily. I wouldn't say that's how it works exactly. It's basically because how far away it is, it takes how long their light takes to travel to us. And like, it's a very direct relationship, I would say. And doesn't exactly change from that or vary.
Do you have a slide on?
Oh, yes. You didn't remind me. I was like, wow. She's like, yes, I do. But yeah, this is a good example. We mentioned redshift before. This is just more of a visual demonstration. So basically, the universe is constantly expanding. And this means that objects that would originally appear in visible light basically stretch and become longer and become brighter wavelengths. And that's why they mentioned before redshift. So now these objects over here, they expand and they get redder. And that means that they are now part of the infrared part of the spectrum. And that redshift, as mentioned, basically allows us to know how far away it is because of that stretch, in a sense, affects the redshift. So all these objects get redshifted over time. is a great way to say it, I'd say. But yeah. Yes.
So this is kind of a methodological
Mhm.
question. You said that it's brand new data, which it sounds very exciting. I'm curious what, Gutta was saying he was looking for the wavelengths and hand selecting
Mhm.
kind of, so it's like more visual. How was your process? What were you looking for? I don't know. Great question.
No, I know exactly what you mean.
Okay.
So mainly I've been, oh, yes. So she was asking about basically the methodology and how with Gutta, it was explained how he looked at the different spectrums and just my general process, I would say. And for my general process, I would say that first of all, I've been working with one galaxy, and that means I've been extracting the spectrum basically pixel by pixel and looking for the different emission lines. That was mentioned before, but just the different like makeups, I would say. So looking at those emission lines, I was able to say, oh, there's a lot of this emission in the galaxy. And those emissions basically tell us more. I've been creating a lot of plots to basically work from that data. Like the mission lets us know about metallicity, the metal content, and it just keeps going further and further, I would say, to learn even more about the physical properties. But yeah.
And I'll just add, Fiona was working with a collaboration in Europe who has a brand new JWST proposal of 14 galaxies or
Yes,
so
it's
in
like
the
around
very
14,
early
yeah.
universe. So for technical folks, redshift 5, 6.
Yeah, 5, 6, 4.
Which is about 1 billion years after the Big Bang or so. So that's how early in the universe we're talking about. The Big Bang was 13.8 billion years ago. So these are galaxies that are already formed pretty well, like 1 billion years after the Big Bang, which is not what we would expect naively before we had JWST. Yeah. Any other questions, or if anybody has questions online, again, please feel free to put them in the Q&A, and I don't see any others, but still go ahead and put them in and we can take questions again at the end. So if there's no other questions in here, let's thank Fiona again. All right, and now I'm very happy to introduce our final speaker for the evening, Nicholas Mazziotti, who's at the University of Arizona, and he's going to tell us, here's the thing, about when giants collide, collisions between galaxy clusters in computer simulations.
Hi, everyone. As Regina said, my name is Nicholas Mazziotti. I'm a rising senior at the University of Arizona, and I worked with Dr. Lindsay King from UT Dallas this summer on a project titled When Giants Collide, Collisions Between Galaxy Clusters in Computer Simulations. So first of all, what are galaxy clusters? Galaxy clusters are the largest gravitationally bound structures in the universe, and they result from hundreds to thousands of galaxies coming together because of gravity. So to put that into perspective here, I have an image seen in visual light, so the light that we can see with our eyes, and nearly every dot in this image is a galaxy. Some of them are galaxies just like our Milky Way galaxy. And you might notice that in these two circles here, there are significantly more galaxies than the rest of the image. And that is because these two circles are galaxy clusters that make up this system called the bullet cluster. Another important component of galaxy clusters is the gas that exists in between the galaxies in the cluster called the intracluster media. And this gas emits strongly in X-ray light, which again is the light that hospitals use to image bones in the body, but we can't see this light with our own eyes. So in this image, the X-ray emitting gas is colored red so that we can see it. And the most important feature is this V-shaped curve right here next to this cluster. And that is what is known as a cosmic bow shock. And this provides strong evidence that this cluster on the right actually collided with this cluster on the left in the recent past, which is what formed that bow shock. And if these clusters hadn't have collided, the X-ray gas we would expect it to be normally distributed. A good way to understand bow shocks is by looking at an image of a bullet traveling through water. So because a bullet is moving at such a high speed through the water in its path kind of piles up and forms this V-shaped curve, which is the bow shock. So this is how the bullet cluster got its name actually. When galaxy clusters collide with each other, when the bow shock forms, this is known as a cosmic bow shock. And the gas along the bow shock gets heated up to really high temperatures that we can actually see with our telescopes. So here is that bow shock labeled again more clearly so that we can see it better. But the physics that are behind a bullet traveling through water are far simpler to understand than with galaxy clusters. So we still don't know how exactly collisions between galaxy clusters influences their long-term structure, which is why it's important to study galaxy clusters to learn more about how the physics of our universe operate on such massive scales. Another important reason to study galaxy clusters is to learn more about this mysterious type of matter called dark matter, which we infer exists in galaxy clusters because we can calculate the masses of these clusters, and we are getting higher numbers than what we'd expect from just normal matter. So dark matter also does not emit any light, which makes it very challenging to detect. To understand this a bit better, I have the total matter of the bullet cluster shown in the purple. And what you'll notice is that the purple doesn't align with where the X-ray gas is, which is significant. So we believe that dark matter is collisionless. It doesn't collide with itself or other types of matter. So when these galaxy clusters collide, the gas will interact with each other, but the dark matter will simply pass through. And this is a really powerful way to study dark matter. In my research, I don't really explore dark matter at all, but an end goal of our work is certainly to learn more about dark matter by studying galaxy cluster collisions. So one place to start to try and answer these questions is by looking at systems where our models don't agree with each other. So for example, we know the cluster masses in the bullet cluster quite well, but in this system known as ABEL 2146 shown here, it's another system of two colliding galaxy clusters with a cosmic bow shock. The methods that we use to calculate the masses in this system don't agree with each other, and we'd like to understand why. The problem with observing galaxy clusters in just about any object in the universe is that things are very far away, and most things don't evolve on human timescales that would allow us to study their evolution. So can you imagine if we could put the universe in a box? That would be a much more efficient way of studying the universe. And that is the essence of simulations, which Naija kind of talked about a bit already. So we can take all the equations that we know about physics and get a computer to solve these equations super quickly, which is what produces the simulation. And then we can compare what we see in the sky to what the simulation produces. And if they don't match, we can go back and tweak the equations until they do match. And this is the power of simulations. And this is especially important for galaxy clusters because they are so complex to study and they contain large amounts of dark matter. Here I have a snippet of a video from one of the simulations that I'm using just to show how realistic it can be. And this video is showing the density of gas on the scale of really large galaxy clusters. So the brighter the color, the more dense the gas is in that region. And what you see are these four massive galaxy clusters that are beginning to collide with each other. And all the other little dots are either groups of galaxies or galaxies themselves. So we can use these simulations to look for these unique merging cluster systems like ABEL 2146 that challenge our understanding of physics. So let's find them in these simulations. The way that we did that was by studying the motions of galaxy clusters in the simulations. And if they ever overlapped with each other, then we consider that to be a merging system. So here I have an example of that. These are two galaxy clusters that we identified as a merging system in the simulation. Using this method, we ended up finding over 1,000 merging galaxy cluster systems. So here I have a histogram to display this information. We have the number of merging systems we identified on the y-axis versus the time in billions of years ago in which the galaxy clusters collided with each other. And the main takeaway is that there's this peak towards the present day, which is indicating that most collisions between galaxy clusters occurred within the last 2 billion years. And this makes sense. It takes a long time for galaxy clusters, because they're so massive, to reach that point and to collide with other really massive objects. Another big discovery that we had was that we found this comparable system to ABEL 2146, which we call a potential analog. So this is an image of that system from the simulation. And what's happening is that there's this less massive cluster in the middle that we think collided with this larger cluster on the bottom right. And what this image is displaying is the temperature of the gas in this system on the scale of millions of degrees Fahrenheit. So the main feature that we can see is that cosmic bow shock on the upper left of the less massive cluster, which is good evidence that this cluster collided with this other cluster. But the masses of these clusters also are similar to Abell 2146, but we still need to do a little bit more investigating before we can officially call this an analog of this system. In particular, we'd like to look at the X-ray emissions and also create gravitational lensing models to study the mass in this system. To conclude, we successfully found over 1,000 merging cluster systems in computer simulations of the universe. And we identified one system as a possible analog to the mysterious Abell 2146 system with common physical features like the cosmic bow shock. But one system isn't enough. We need to keep looking for analogs to study Abell 2146 further. And that is it. Thank you.
Great job. Let's see, opening it up to questions. And again, I'll just say if anybody on the Zoom has a question, go ahead and put it in the Q&A. Yeah, go ahead and remember to repeat.
Oh yeah.
So it seems like it was a lot of work to find those 1,000 galaxy cluster merging things. So is that data that you plan to like publish or put out as a data set? Because that just seems like it would be helpful for other people to have.
Right. Okay. So the question is, we found all these galaxy clusters. Would it be helpful to publish these clusters so that other people can look at it? And definitely, it'd be like a longer term goal right now. But with these systems that we're looking at, we're one of the first people to actually look for merging cluster systems in these simulations. One of the simulations we're looking at was actually released last year. So it's a very recent effort, and we are comparing with some other catalogs too that people have done to look for merging systems. And we definitely think that publishing our catalog will help people in the future look for these mergers.
My question is that I think your graph showed that there are more collisions happening more recently.
Yeah.
And I was wondering why you think that is. If the universe is expanding, wouldn't the galaxies be getting further apart?
Okay, great question. So the question is, in this graph, we see more frequent cluster mergers in the recent 2 billion years ago, but the universe is expanding. So wouldn't we expect there to be less cluster mergers? And so it's a kind of complicated question to answer. The clusters that are close enough to other clusters right now will definitely like be able to still interact with each other. The scale at which like the universe is expanding is a bit too big to drive these clusters like too far apart that they can't collide. And then the reason that this is peaking so much like towards the present day is just because these clusters, they get so massive and then they tend to be around like the other massive clusters too. And so they won't really move too far apart in that amount of time.
So if like the rate of expansion then isn't enough to keep them from colliding, then like at one point, like, and then I assume like if they get bigger and bigger, there's more gravitational pull, so they're stronger, they could pull more stuff in. So eventually it would just like everything squish together, or is everything going apart, or is it both at once?
Right. Okay. So the question is, so since the expansion of the universe might not be enough to actually push things apart, will eventually everything just come together because they seem to be colliding still? And the answer to that is kind of, it's hard to say. Galaxy clusters can actually like form like larger structures, which we call superclusters. And these are definitely like extremely like large objects that we think that are like the main structures of the universe. Will everything collide together? I can't say for sure. But these superclusters seem to be that main structure that these collisions might be working their way towards.
Simulations you showed, what's the like time scale to that like few seconds?
So yeah, no, that's a great question. So this snippet, it was from like a minute long video, which is supposed to be, the entire history of the universe. So like 14 billion years, this is like 10 seconds of it, which is still like a few billion years, like not as much as that. But, and this is later, this is more closer to the present day. Yes.
Why do galaxies collide? Are they just on a trajectory and they happen to collide, or are they drawn to each other?
Right. So they do have like initial motions like after they form in like the early stage of the universe, but eventually the mass is really driving like their dynamics and things like that. So the more massive that they grow, the more common it is for them to be colliding and attracting many things. So there could be like a really massive thing over here and then a less massive thing like really far away, but if there's nothing else pulling it, it will just keep going towards that. And so it's really just the mass that is like driving all of these collisions. And we can see that really good here with all those little galaxies like just being pulled in. They're not moving fast enough to escape that gravity. Yeah.
Do you find more galaxy clusters with objects that are like blue shifted, like going towards us?
Oh, that's a good question. I have no idea. I haven't really looked at like galaxy clusters moving towards us. I know that like we are roughly within like 50 million light years of the closest galaxy cluster. But I'm not sure if that's moving towards or away from us. With the simulations, it's kind of hard to tell because there's no like vantage point or anything like that. But no, that's still a good question and something that would be worth looking into.
This might be a silly question, but like, how catastrophic is the collision? Like, is it
Oh,
boom?
yeah. So no, that's a great question. So we think that like when galaxy clusters collide, that is like one of the most energetic processes since the Big Bang. So this is injecting like an incredible amount of energy into just like the cluster itself and the galaxies. This is actually influencing the galaxy evolution too. So it's an incredible amount of energy.
Yeah. So, not knowing anything about any of this, when I was a kid, space was like empty. And the more we can see, the more it's not empty at all. So if it's expanding sort of away in time, expanding into what? If it's
Okay.
full, how could it, well,
Right. So we could talk a little bit about that. So this involves dark energy, and that relates to the expansion of the universe. I'm no expert on dark energy, so I can't say too much about what it's expanding into. We definitely don't know that right now. If anything, space is expanding into itself, which makes it's kind of hard to like wrap our head around that. But yeah, we think dark energy is like a force that is the opposite of gravity. So it tends to push things away instead of pulling them together. And that is what we think is responsible for the accelerated expansion of the universe, which I try to have here. But that, yeah, it's a really big scale. And so no one knows for sure.
You got the deep question. I'm going to put one last call. We had a congratulations, great job to everyone in the Q&A. If you're out there in the Zoom world and you have any last questions or comments, go ahead and do them now. And this can be for anyone. I'll open it up and actually to the room here as well. And while we do that, I'm going to put up our final slide. All right, I don't see any more questions in the Q&A, so I'm just gonna thank everyone who's still there online for coming. Thank you so much. We will be posting the recording of tonight's event on our YouTube channel in a couple of days, so if you missed it, or if you want to share it with anybody, the recording of tonight's event will be available. And so I'll thank everyone who's online for tuning in, and for everyone here in the room. You're welcome to hang out for a little bit, and we are happy to chat. And if you have more questions, we will hang out for a bit, and then we will go up to open night. There is going to be an open night tonight, 9 o'clock up at Loins. Not clear if it's going to be clear. So we'll either be doing our cloudy presentation, although I see some blue sky, so it might be okay. So thank you all for coming and thank you for all your great questions, and mostly thank you to you guys for working so hard, and also to Naija who's on the Zoom. But I don't know if we can get Naija's video up. There's Naija. All right, thank you so much. Bye everyone online. Thank you all. Stay there.